So technical contradiction matrix is one way to do it. So for example, let us take this slide from NASA, Glenn Research Center, where they say, okay, if I increase the area of the wings, my lift increases. So I can actually, fly much faster. I can have I can have bigger aeroplanes. I can carry more weight because my lift increases. But can you just increase the area of the wings? No. As soon as you increase the area, what happens? The weight of the wings also increases. So you wanted to, for example, you wanted to carry a payload of you presently carry a payload of 100 tons. You wanted to carry 200 tons. So you said, let me double the area of the wings. Now what happens? As you double the area of the wings, the weight of the wings also increases. So instead of 200 tons, you will still be able to carry only 170 tons, let us say. Not too good, no? So somehow you want to increase the lift without increasing the weight of the wings. Are you able to see this? Is this a kind of contradiction you would also face in your workspace? Have you seen such stuff? Oh, I can have parallel processes running, but then the memory footprint increases. I need much more I need much more RAM. Has it happened with you? Hello? Okay. So now what we do is we formulate the engineering contradiction. We start to write the problem in a format of if, then, but. For example, if we increase the size of the wing, then it generates more lift. But the weight of the wing also increases. Okay. So whatever problem you have, you formulate it as a contradiction. That is the first step to applying the inventive principles. You formulate the problem as if, then, but form. Okay. Once you have it like this, then you actually generalize. What is generating more lift? More force, let us say. And weight is generic enough. So you go to the next sheet and you say, I want to generate more force, where the weight of the moving object should not, or weight of the object should not change. And you see there are these 4 inventive principles mentioned in that column. The principles are anti-weight, sedimentation, thermal expansion, and mechanical vibration. So now you set to think of, now you apply the force fit ideation technique that we discussed in the last class. What was the force fit technique that we discussed in the last class? Can someone remind me? Hello?
So integrating one properties of a particular thing that is totally unrelated to our problem.
So we gave a clue which I could not directly associate with my problem statement. That was what we did.
Yes, sir.
And then we saw how to find a solution.
Yes.
So now you may think thermal expansion has nothing to do with this wing and force wala problem. Hai na? You go sit together as a team, form 2 teams, do the force fit game and connect each one of these principles to your problem statement. And you will come up with solution ideas. At times, you don't even need to go to force fit. You read the idea, you read the inventive principle, and bingo, you get the solution ideas right there. If not, use the force fit method. Okay. So now you think of how to do it. So let us look at the details of these inventive principles. Anti-weight says, merge an object with other objects providing lift. Make an object interact with the environment such that you get to use aerodynamics or buoyancy or other forces. Segmentation means divide the object into multiple independent parts. Make an object easy to disassemble, increase the degree of fragmentation or segmentation. Thermal expansion, use thermal expansion or contraction of materials. Use multiple materials with different coefficients of thermal expansion. In one of the office hours, we talked about bimetals. Remember, where we said two metals are kind of pasted together. Each has a different coefficient of thermal expansion. As the temperature increases, let us say the top metal expands more, the lower one lesser. What happens? Your material becomes like a curved thing. So you have more surface area inside. The pressure inside your chamber could reduce. If you were to use this, you could use the same thing, for example, if this was a wall or this was a window, then bimetals would simply open the window for you. We talked about this in terms of building greenhouses. Is someone from that team over here in the class today? Okay, doesn't matter. But thermal expansion, use two materials so that you could get the function done easily. We can't use it for the aeroplane though, but yeah, the inventive principle I was just sharing. And mechanical vibration, there are details of the mechanical vibration idea also. And the principle was solved, the problem was solved by actually moving the air near the wings in a spiral manner. This is a US patent. So they moved the air in a spiral manner. So air would enter over here, enter the wings from here, and it would go out in a spiral manner. And what that does is that for the purpose of air, this then kind of extends the dimensionality of the wing. The size of the wing increases, but the weight doesn't. Because the effective size of the wing has increased, the lift improves, but the weight of the wing does not. Okay, and this is a US patent. Let us look at another example. This is a Turing machine. What does a Turing machine do? It removes stuff from materials. It kind of polishes it, whatever it does. It forms those rings on your material, and when you do that, there are shavings. Even when you sharpen the pencil, you get the shavings. So what happens is that on the belt and on the Turing machine, there are lots of shavings that fall. And when those shavings fall, what happens? The Turing machine gets clogged at times, and then you have to stop the Turing machine and you have to clean that up and then restart the operation. This is not desirable. I want to remove sorry, it's not Turing, it's turning machine. I want to remove the shavings from the turning machine without using complex robots. So the problem is, if one were to use special robots for removing these shavings, then the shavings would be removed and the process would be stable, but the applied equipment would be very complex and expensive. So what do we want to do? We want stability, but we do not want the cost or complexity to degrade. Are you able to see this? So whatever the then and but parts are, you kind of try to generalize them. So you want to improve process stability, but do not want to degrade the complexity of the system. So you come to a little more generic parameters. Process stability, they say, use the term as reliability. Complexity, in that particular table, we will look for complexity of the device. You go to the table, row number 27 talks about reliability, 36 talks about complexity. The inventive principles that are written there are 13, 35, and 1. 13 means do the other way around, Where else did we see this inventive principle? We've already seen this inventive principle earlier many times. Do you remember?
Sir, in the
Sir, when the
chocolate
very
candy
starting,
adapter.
yes, sir.
Yes, the examples where we talked about Nina trying to get those chocolates made or polish those
College
nuts
balls.
and bolts and all that. Hmm? So other way around principle, you remember. What does it say? It says invert the action. Invert the action, make movable parts fixed, fixed parts movable, turn the object upside down. The second one is change physical or chemical properties. Change the object's physical state, move it from gas, from solid to a liquid or to a gas. Change the concentration or consistency, change the degree of flexibility, change the temperature. That is 35. Principle 1 is segmentation. Divide an object into smaller parts, independent parts. Make the project easy to disassemble. Increase the degree of fragmentation or segmentation. So, can we think of a solution by using segmentation? I need to clean this. I need to clean this turning machine and remove the shavings. How can the principle of segmentation help me? Have you cleaned small crevices of your laptop or something like that? Laptop or keyboard, have you tried to clean? What happens? Hello?
Yes, sir.
What is the problem when you try to clean these small spaces?
So the dirts that are present in between the keys and stuffs, they need to be cleaned in some other fashion.
Yeah, it takes a lot of time, it takes a lot of time. Now let us say if I could disassemble the keys like this, I just press a button, all the keys come out. Would it be easier to solve the problem?
Yes, sir.
So that is where segmentation, divided into parts which are easy to disassemble and bring back. If I could do that, I could very simply clean the keyboard. Until that time, it is very difficult. So something like this could be applied to the turning machine also. Can you do that? जहां पे भी shavings अटकती हैं, wherever the shavings get stuck, make those parts disassemblable. Make them easy to disassemble. Then the cleaning part would be fast. But is there a better solution? Is there a better solution? If I say that I could turn the object upside down, what happens? See, when it comes to people, you cannot have people go upside down. But this is a machine. Instead of keeping the machine on the floor, you can hang it from the roof. The shavings would automatically fall down. They will not fall on the machine. Nothing is required. You've used the principle of gravity, a resource which is so commonly available, and you solve the problem. Are you able to see this? Any questions?
Yes.
You want to see one more example? Let us say a styling comb. So a styling comb has some gel in it. So we want to increase the life of the styling comb. So we want to increase the quantity of gel that it has. But then with that, the weight of the comb would increase. So this is not something we desire. We come to a typical engineering contradiction where we say quantity of gel is something like quantity of a substance. Weight of comb means weight of moving object. And you look at the table and you see that, okay, these are the 4 principles which are commonly used to solve the problem. You could use universality, you could use mechanical vibration, porous materials, or parameter change. We applied all these different principles one by one. Finally, we said, if I could change the state of my object, of my gel, I could do something. So first we looked at porous materials. I had to reduce the weight, so we would drill small holes into the handle so that the weight reduces. To apply the parameter change idea, what we said was store the gel by dehydrating it. Now, when you are combing wet hair, you would get water from the hair itself. That water, you use capillary action. Use capillary action to get the water into your gel, and then this gel gets released, and you can comb your hair, style your hair with that. Okay, so you're using the water in the hair itself to comb your hair. Now there's a lot of material, gel material, which is there that can be stored without increasing the weight of the comb there. So solidified hair gel is used instead of liquid gel. Okay. Got a fair amount of an idea of how to apply technical contradictions, how to use technical contradiction matrix to identify inventive principles.
Yes, sir.
Yes, sir. Yes, sir.
You want to see one more example of a circuit, let us say?
For sure, sir.
I'm a circuit designer, so I have circuit examples also there. So
Yes.
this is a 6T SRAM cell, 6 transistor SRAM cell. When you want to write into the SRAM cell, what happens is, so there are many constraints. One of the constraints of designing a good SRAM cell is that this particular PMOS has to be very weak. Now, you store a 0 and a 1 inside the memory cell. If the PMOS is weak, the PMOS would transfer a 1. If the PMOS is weak, the current would be less. So the write time degrades. If the PMOS is strong, then you have some other constraint. The writability goes for a toss. So you want the PMOS to be weak and you want the PMOS to be strong. That's a different thing. So what we said was that the side on which I have to store a 0, the PMOS should be weak. But the other side, it should be strong. So how do you do it? We looked at the technical contradiction matrix. We said, okay, we want it to be strong to improve the speed. But as I improve the speed, the strength degrades. The strength comes to a place where I'm no longer able to write a 0. So I do not want that. So the principles that were listed there were counterweight, local quality, copying, and spheroidality. Now, just like in the last example, not all principles you will be able to find solutions with. So I picked up 2 principles, local quality and copying. And by using these principles, we added 2 additional PMOSs here where, okay, I'm not going into the functionality, where you would be able to get additional strength. So to write a 0 into this memory cell, you take this node to 0 and continue with this node at 1. Okay. Now, this might be latent for many of you, but those of you who understand circuits, just for them, they will probably understand this. Okay. So what happens when I want to write a 0 here, this PMOS turns on, that improves the strength on this side, whereas this PMOS continues to remain off. So only when you needed it, there was additional strength available, and you also used the principle of copying to arrive at this new memory cell, which was also patented.